Hello, my dear students. Welcome to the next subtopic of semiconductor chapter. And we are learning special purpose PN junction diodes. In the lower standard 11th standard, we understood the normal PN junction diode, which was used for unidirectional flow of current. That means if suppose it is forward bias, then only the current will be allowed, while in the reverse bias condition, the current was blocked. Then in this 12th standard, we started with the special purpose PN junction diode. We started with the first Zener diode. The Zener diode is the diode um, which actually works as a voltage regulator in reverse bias condition. So we have to attach this Zener diode in the reverse bias condition. Next, we understood the photodiode. The photodiode is the diode which operates, that means which conduct electricity when a photon of particular energy it falls on its depletion region. Okay, and the next special purpose PN junction diode that we are going to learn in this session is a solar cell. So what is a solar cell? A solar cell is, we all know that it is a device so which converts electrical energy, which converts solar energy into the electrical energy, right? So the device which converts solar energy into electrical energy, the sunlight into the electrical format, this is called a solar cell. Now the solar cell, how it is made? It is made just like a PN junction diode. So the structure of the PN junction diode in the case of solar cell is different as compared to the normal PN junction diode. Also, we will learn how this solar cell it is used to store energy, it is used to store power, it is used to store electric power, and later on it can be applied to the external load if it is connected to the external load and the current electricity how it flows through the solar cell, what is the mechanism of the solar cell, what is the working procedure of the solar cell we are going to learn in this session. So the next topic here is the solar cell. So solar cell is pollution free and available free of cost. Free of cost indicate it is cheap. So almost all the semiconductor devices are very cheap. Okay, so the IC which is used as a temperature sensor in your refrigerator, it comes under rupees 15 cost. Okay, so this is a very cheap electronic component. The semiconductors are so almost all semiconductor devices are very cheap. So they are purchased in bulk, or we can say they are since made up of silicon, they are very cheap. Okay, now it is pollution free. Pollution free means whenever we consider the conversion of electricity, so it results into some pollution. Okay, it results into some pollution. But the solar energy conversion considered to be in the form of solar cell, it is pollution free. So it does not result into any heat pollution or any noise pollution or any other pollution. So solar energy is pollution free and available free of cost. So whatever the sun rays, the energy which is coming from the sun, it is pollution free and it is available free of cost. Sun is the environment is not charging us anything for oxygen, for light, for energy, for heat, anything. The environment is not charging us. Okay, so the solar energy is pollution free. Also, it is available free of cost. So we should utilize it to convert into electrical energy. Okay, since it is available free of cost, it will be very cheap for us to convert it into electrical format. So we can use this solar cell in two ways. The first one is the photothermal devices. So what are photothermal devices? So these devices are used to convert the solar energy into the heat energy. Okay, so the solar energy is getting converted to heat energy. These are mostly used for providing hot waters. These photothermal devices are usually it is used for providing hot water because it is used to convert the solar energy into the heat energy. But our topic is something else. We do not want solar energy to get converted to heat energy. We want solar energy to get converted into electrical energy, and that is the next device that is called as photovoltaic device. So solar cell, it is also called as photovoltaic device, or we can say photovoltaic cell. Solar cell, it is also called as photovoltaic cell. So what are photovoltaic cells? Photo means photons. Photons means what? Light. Thermal means heat energy. Voltaic means voltage, current. Okay, that means electrical energy. So photovoltaic means photons to electrical energy. Photothermal means photons to thermal energy, that is heat energy. Okay, so photovoltaic devices, these are the devices which use to convert solar energy into electrical energy, which can be utilized, which can be done using the solar cells. So what is the light incident on the solar cell produces both current and the voltage. So light incident on the solar cell produces both current as well as voltage to generate electrical power. So the solar cell thus works as the source of DC power. So what is the solar cell? It is utilized. See, you will be having a voltage source, or you will be having a current source. Okay, these are the two sources. But solar cell has both voltage as well as current source. Okay, so voltage, if it is multiplied by current, it will result into power. So we can say power is equal to voltage multiplied by current. We can say that solar cell can be utilized as an electrical power. Okay, so it is used to generate the electrical power. So what solar cell work like? It just work like a DC power. So just like you are connecting a DC power, that means you are connecting a solar cell. Solar cells can supply power for electrical equipments at remote place on the earth, or abroad, a satellite or a space station where the normal electric wire connection is not feasible. So in the remote places, like in the village places, uh, underdeveloped places where the power lines cannot be drained. Okay, so in that case we can use the solar energy. We can use solar cell to convert the solar energy into the electrical energy, and we can supply the electric power to the remote places. Also, in the case of satellites or the space station, the electrical energy or electrical power, it is actually supplied by using the solar cell technology. So solar cell, the structure of the solar cell, how it looks like. So normal PN junction diode, how it looks like. This is the normal PN junction diode. This is the silicon substrate. This is the silicon substrate. On this side, the p-type impurities are doped. On this side, the n-type impurities are doped, and in between there is a formation of junction. Now, the power of the solar cell, the voltage stored by the solar cell, or the current stored by the solar cell, it depends on the length of this depletion region. It depends on the length of this depletion region. So it was decided that the design of the solar cell can be like this. Suppose this is the N-type substrate, this is P-type substrate. So like this, we are getting the depletion region, such that the length of the depletion region, it is now more. So if suppose the length of the depletion region is more, that means more amount of voltage, more amount of current, or I can say more amount of power, it can be stored into the solar cell. Okay. So structure of the solar cell. What solar cell looks like? The solar cell looks like this. So see here, this is the normal PN junction diagram, right? I can say this is the N type. I can say this is the emitter N type, and this is the base. I can say it is P type, right? So there is an emitter and there is a base. Emitter means going to emit electrons. Base means it is going to collect that electrons, and it will obviously provide the holes because it is the p side. Now see, p side, the area of the p side is very 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 high, but in the area of the n side is very very less. This is the depletion region. This is the depletion region. You can say that the length of the depletion region is very high because the first p side p type impurities are doped, and on the other side n type impurities are doped, and because of this, the length of the depletion region is very high compared to the normal one. Now, in order to get the electrical connections, this is the rear contact, the back side contact. So since it is connected to the P side, that's why it is positive. While this is the front contact, the front contact electrodes are there since it is connected to the N type of semiconductor. That's why I can say it is negative, right? Then the anti-reflecting coating is there, anti-reflecting contact is there. That means whenever the sunlight is going to incident on it, So it won't will be getting reflected, but it will be transmitted, or we can say it may be absorbed. So anti-reflecting means, see, whenever the light incident, there is only three cases. The first is absorption, the second is reflection, and the third one is transmission. Okay. So whenever the light is getting incident on any object, there are three cases only. The first is absorption, the next is reflection, the third one is the transmission. Transmission means that suppose the light is incident, it will transmit it and it will move outside through the body. Reflection means it will be getting reflected from the surface of the body. Absorption means it will be getting absorbed into the body. So this has to be avoided. The reflection has to be avoided. Okay, so that's why the coating is actually the anti-reflecting coating. Okay, so this is the structure of the schematic structure of the solar diode, solar cell, I can say. So this is the solar cell schematic structure. So what are the materials which are used for fabricating the solar cell? Material used for the fabrication of solar cell should fulfill the two important requirements. So what are the two important requirements? The first requirement is it must be a photosensitive material. Photosensitive material means it should sense the photons. Okay, that means if suppose the photons are getting incident on that material, it is going to emit charges. It is going to emit charges. So whenever the photons get emitted, get incident on this depletion region, it will emit charges. So in the semiconductor, the charges are actually free electrons and holes. So they have to generate free electrons and holes. Okay, so it must be a photosensitive material. That means what? Which absorbs light and raises what? Electrons to a higher energy state. Okay, that means higher energy state means the conduction region, conduction band. So that means the electron will get free. That means the electron will get free and it will be available in the higher energy state. The next requirement is the higher energy electrons thus generated should be taken from the solar cell into the external circuit. So that means why it should be taken to the external circuit, because there can be a chance that if suppose the electron is getting incident, it is getting generated inside this solar cell. There can be a chance that it will recombine with the pole, and that will be that I can say no amount of current will be flowing to the external circuit if it recombines with the holes. So what is the second requirement? The second requirement is the higher energy electrons, that means the free electrons, thus generated in the first process, should be taken from the solar cell into the external circuit. So how it could be done? The electrons then dissipate their energy while passing through the external circuit and return to the solar cell. So just like a battery normal cell, just like a normal cell, I can say. So this is the external circuit. The electrons are getting emitted from the negative charges. It will be moving to the external circuit, and again it will come back to the cell. So again the same thing they are asking. Okay, they are telling the same thing. The electrons then dissipate their energy while passing to the external circuit and return to the solar cell. So almost all photovoltaic devices such as semiconductor material in the form of PN junction. So almost all photovoltaic devices, what it uses the semiconductor materials. So almost all photovoltaic devices, that means the devices which is used to convert the solar energy into the electrical energy, they are made up of semiconductor materials in the form of PN junction, which can be seen in the diagram. Okay, so you can pause the video, you can write the things down. Suppose you have any queries, any part you are not understood, you can again watch this video. Okay. So I'm moving to the next slide. So what is the working of the solar cell? The working of the solar cell is very clear. The material used for the fabrication of the solar cell, they are actually the photosensitive material. That means whenever the photons of particular energy will get incident on the depletion region, so in that case, or in the P region or in the N region, in that case, there will be a formation of electrons and holes. There will be a formation of electrons and holes. So when light is incident on the solar cell, the following sequence of events take place. So what happens actually if suppose the light is getting incident on the solar cell? The first one is The electron hole pairs are generated in the depletion region of the p-n junction. So these are called as photo-generated carriers. So photo means photons, that means light. So because of this photons or light, I can say the electron hole pairs are generated in the depletion region of the p-n junction. So these are called as photo-generated carriers. If suppose the light is getting incident on the depletion region. Electrons and holes are separated and they are collected at the cathode and anode respectively. That means electrons are getting collected towards the cathode and the holes are getting collected towards the anode, okay, respectively. Okay, that means the cathode which is negative, it will become more negative, and the anode which is positive, it will become more positive. So this will charge the battery. That means more positive, more negative means it is going to charge the battery, charge the solar cell. The carriers are accumulated and generate the voltage across the solar cell. So the carriers are accumulated means it will form a group. Okay, the carriers will accumulate. That means electrons will get accumulated in the cathode region. That means the N region. Holes are getting accumulated in the anode region. That is the P type of semiconductor. So the P type of semiconductor, more number of holes are present now. In N type of semiconductor, more number of electrons are present now. So that is going to result into large amount of holes and electrons, and thus you can say the voltage or the current or the total power across the solar cell is going to increase. The fourth point is the power thus produced is dissipated, utilized in the load resistance or in the external connected circuit um, across the solar cell. So whatever is the power or energy or the voltage which is generated in the first, second, and third case, it can be utilized or it can be used to dissipate that power whenever it is connected across the load resistance. So whenever the load resistance is connected, so the electric current will be flowing, it will start flowing to the solar cell, and it will be providing power to the external circuit. So this is the working procedure of the solar cell. So all of you know these things, this very important thing. The next is the structure of the solar cell, how the solar cell looks like, and how this actually works. So you can see this whenever the light is getting incident on the depletion region. This this is actually the N region, which is very thin, while the P region is very thick. This we have already understood. Okay, the depletion region here it is there, and because of the light which is falling on the depletion region, there is a formation of electrons and holes pair like this. There is a formation of electron and hole pairs. Now what happens actually, this holes will be getting pushed towards this P region, and this electron it will be getting pushed towards this N region. It will be coming out of the depletion region. Okay, so again this P, the positive will be there in the P region while the negative will be there in the N region. The positive will be there in the P region and negative will be there in the N region like this. So this will be more negative and this is going to be more positive now. So that's why it can be used to get it is used to supply the current. So it will be going from positive to negative like this. The current will be going from positive negative to the external load resistance applied to the external load resistance applied. So structure of the solar cell. Current produced in the solar cell is called as the light generated current, or we can say it is the photo generated current because photo is nothing but what light. The photo is nothing but light. So light generated current or photo generated current. So this is the two-step process. How it will be light generated current or photo generated current it is actually produced. The first step is the absorption of incident photon to generate the electron hole pairs. So there will be an absorption of incident photon, the first step. The electrons and hole pairs will be generated in the solar cell provided that the incident photon has energy greater than what? It should have the energy greater than the energy band gap. So if suppose it has the energy greater than energy band gap, then only the electrons from the valence cell it will be jumped to the conduction cell. That means it will be called as the free electrons or it will be available for conduction. So because of this only, you can say the solar cell is going to charge. So the condition is the incident light should have the energy or energy greater than the energy band gap of the semiconductor device choose in the substrate region. So electron hole pairs will be generated in the solar cell provided that the incident photon has the energy greater than that of the band gap. Normally what happens, the electrons and holes does generate, does produce recombine and will get lost and will be lost. There will be no generation of current or there will be no generation of power. Okay. So normally what happens, the electron and hole pair thus produce because of this light energy recombine and will be lost. So this should be avoided actually. This should be avoided. Okay. Because if suppose the electron is getting generated anywhere in the PN junction, the special purpose diode or the solar cell. So there can be a chance that the electron and hole will recombine there and the total charge will be lost. So this is the drawback. This has to be avoided. Okay. So how to avoid this? In order to avoid this, only we are considering the length of the diffusion region should be more, such that there should be a space required for the positive ions to move towards the P region and the negative ions to move towards the N region, and they both will recombine by themselves. So if they recombine with themselves, there won't be any generation of current or power. Okay. The second point is, however, the photo-generated electrons in the P region, okay, and the photo-generated holes in the N region are specially separated. Specially means there is a space. So there is a more space between the P and the N region. I can say that's why the length of the diode it is more. They are specially separated and prevented from recombination in the solar cell. So because of this, these are the two steps in which the photon generated current or we can say light generated current is produced. This separation of carriers is possible due to the intrinsic electric field. So because of the intrinsic electric field, that means the electric field because of the minority charge carriers. So I hope you remember that there is a no additional voltage required for minority charge carrier to cross the junction. The forward bias voltage 0.7 volts for the silicon substrate is required um, to cross the junction by the majority charge carriers, while minority charge carriers do not require any extra energy to pass the junction. So that means they have their own electric field that is called as intrinsic electric field. So because of this intrinsic electric field only, the separation of charge carriers are possible. Okay. So when the light is generated electron in the P region, so it was there actually in the wrong region, right? Reaches the PN junction. So because of this intrinsic electric field, it is because the electron in the P region is the minority charge carrier. That means it can pass the junction. Okay. So it reaches the N region where it is now the majority charge carrier now. Now it won't will be able to cross the junction because it is the majority charge carrier, right? Similarly, what happens is the light generated hole reaches the P region. So light generated hole in the N region actually is the minority charge carrier. It reaches the P region and it becomes the majority charge carrier in it because of this intrinsic electric field only. And it is not going to come back to the N region because we are not supplying any external power to the solar cell, any external voltage to the solar cell, such that if it is greater than 0.7 volts, then the current will be passed through the solar cell. Okay, so we are not doing this. The positive and negative charges are thus accumulated on the P region and N region of the solar cell, which can be used as a voltage source. So this solar cell can be used as a voltage source or it can be used as a DC power source. When the solar cell is connected to the external circuit, like the example which is shown in the diagram, so if it is connected to the external circuit, the light generated carriers flow through the external circuit. So it actually flows to the external circuit. So whenever a load resistance is connected, so the current is it will start going from positive terminal of a battery towards the negative terminal of a battery like this. And what happens inside the solar cell? Inside the solar cell, the current flows from negative to positive. That means the current always flows from positive to negative, but inside the cell, always the current flows from negative to positive. Okay, so that means this is the reverse current. Reverse current means the current in the solar cell is negative. Okay, remember this. Current in the solar cell is negative. So what is the VI characteristics of the solar cell? So since the current is negative, I will draw the current here on the y-axis. It is there on the negative direction of y-axis. The voltage we are getting from the solar cell is positive, so I can this is the positive voltage. So suppose I consider this point. This point means there is zero current. So whenever the current is zero, that means the no load is connected. No load is connected. That means it is open circuit. So that means voltage, whatever we are getting is the open circuit voltage. While if suppose the current starts flowing to the device, that means load is connected. So this is called as the current in the reverse direction. I can say ISC. ISC is called as the short circuit current. So the characteristics look like this. This is the characteristics which looks like okay. So this is there in the fourth quadrant. This is there in the fourth quadrant. Okay. Or if you please pause the video, you can draw the diagram. Here in the textbook, it is drawn in the first quadrant, but it is written that it is there in the fourth quadrant. Okay, so see here, what is there in the diagram? So there is a current on the y-axis, there is a voltage on the x-axis. So this example, it is a particular solar cell. So no need that all solar cells will be having the same specification. So here we are getting the open circuit voltage VOC, and here we are getting the short circuit current that is what ISC. So here we can say this is the maximum power which is generated, and maximum power is nothing but the maximum voltage Vmax multiplied by Imax, because power is equal to voltage multiplied by current. So power is maximum, if current is maximum, also the voltage is maximum. So maximum power, it is equal to Imax multiplied by Vmax. So this is drawn in the fourth quadrant. It is written that it is drawn in the fourth quadrant, but actually it is drawn in the first quadrant. Okay, which is wrong. It should not be drawn in the first quadrant. It should be drawn in the fourth quadrant. Okay, so you have to replicate this y-axis in the negative direction. Okay, so just only the proper one draw. Just only draw the proper one. That is nothing but the already cut, right? That is nothing but the already um, I explained you the fourth quadrant diagram. Okay, so you draw that fourth quadrant diagram only, and you can use the specification which is used in this. Okay, so this is drawn in the fourth quadrant because the solar cell supplies current to the load. That means inside the solar cell, the current flowing is the negative. Okay, that's why it should be drawn in the fourth quadrant. The power delivered to the load is zero. When the power delivered to the load is zero, when the load is short circuit, okay, or it is open circuit. So in the case of short circuit or open circuit, the power delivered it will be zero. The intersection of the curve of the I-axis is the short circuit current. So whenever you can say the intersection with respect to y-axis is nothing but ISC, ISC is nothing but short circuit current. So here the curve it is actually getting incident, it is getting touched, or it is getting intersected with the respect to y-axis. So this is called as the ISC, the short circuit current. Okay, corresponding to the given light intensity. So this is all discussion. It is with respect to a given light intensity. So if suppose the light intensity is changed, so this specification or specification will change. The graph will change. The power delivered to the load is zero when the load is short circuited. The intersection of the curve with respect to I-axis is the short circuit current, which is generated by ISC, while corresponding to the given voltage, corresponding to a given light intensity, the intersection of the curve with the y-axis, or I can say x-axis, or I can say the voltage axis is the open circuit voltage, which is denoted by VOC. Okay, so the corresponding to the given light intensity, again the power delivered to the load will be zero when the load is open. However, if suppose the point on the curve where the power delivery is maximum, so if suppose the power delivery requirement is maximum, I can say P max is equal to V max multiplied by I max. V max multiplied by I max. So where V max is this value, I max is this value, which is shown in the diagram. This is the V max value, this is the I max value. So if you multiply this to V max and I max, you will be getting the maximum power. You will be getting the maximum power. So maximum power V max, that is equal to V max multiplied by I max. Okay, all of you are requested to take the screenshot or you can write things. Okay, I'm moving to the next slide. So what are the criteria for selecting the material used for the fabrication of solar cell? So suppose you want to make your own solar cell, what important criteria you should keep in your mind? The first is its band gap should be between 1 electron volt to 1.8 electron volt. So the substrate that we are going to consider, their band gap should be between 1 electron volt to 1.8 electron volt. It should have high optical conservation of light into the electrical energy. So optical absorption should be high. So that's why it is coated with the anti-reflecting material because reflection it will be avoided and the absorption and transmission it will be more. So it should have the high optical absorption, conversion of light energy into the electrical energy. It should have a good electrical conductivity. So semiconductor material it is chosen in such a way that the electrical conductivity is more. Material should be easily available, and most material used in the fabrication of solar cell have a band gap of 1.5 electron volt. This includes silicon. For example, the band gap is 1.1 electron volt. Gallium arsenide, the band gap it is equal to 1.43 electron volt. CDTE, the band gap is 1.45 electron volts, while CuInSe, the band gap it is between 1.4 1.04 electron volts. So ideally it is between 1 electron volt to 1.8 electron volt. Actually it is 1 electron volt to 5 electron volt, right? So solar cell used in the domestic and space applications are mostly you can say they are silicon based solar cell, and the solar cell are non-polluting, means it does not result into any noise pollution or sound pollution or any type of wastage. They require less maintenance. So maintenance cost of the solar cell is also very less. But initially you can say that initial installation cost is very high and last longer. That means there is a very less chance that the solar cell it will get damaged. Okay, so solar cell is going to last long and they have higher cost of installation and are low in efficiency. The cost of installation is more and the efficiency is less. Okay. What are the applications of solar cell? The first application is the solar cell are used for charging the batteries, um, which that batteries can be utilized in the night time. Okay, so the first application is the solar cell are used for charging batteries during the daytime, so that batteries can supply power during the night. So they are useful at remote uh, places for supplying power to the various electronic equipment from the calculator to the satellite and the space station to supply power to the traffic signals in communication status and in the lux meter, which is used to actually measure the intensity of light. Remember that in the lux meter also we will be using the solar cell, and this can be used for measuring the intensity of the light which is getting incident. Okay, so this is all about the solar cell. The next topic we are going to learn is the light emitting diode, nothing but called as LED. Thank you so much, all of you, for paying attention. Keep learning, keep smiling. Goodbye.